This webinar is intended for the non-GIS folks, and it focuses on one aspect of GIS, and that is LiDAR data and the derivatives. Today we are really fortunate to have four presenters. Steve Nechero, Geospatial Data Management Branch Chief. He'll present the basics. What is LiDAR? Aaron Dushku is a GIS specialist in Massachusetts, and he'll show us how the field can use LiDAR-derived contours. Reed Sims is a GIS specialist in Vermont, and he'll show us how LiDAR-derived elevation data are really important in our fieldwork. And Steve Crabtree, a GIS specialist in Kentucky, and he'll introduce a tool which estimates water runoff needed in order to design conservation practices. And now, Steve Nechero, you may proceed.
Thank you very much. It's a pleasure to be here this afternoon to talk about LiDAR. Let's go ahead and get started. NRCS has been using geographic information systems for many, many years, and you have to think of GIS as a layer cake of geospatial information that describes the environment and different aspects of agricultural activities. The thing we're going to focus in on today is basically the base map. And our base map is made up of the National Agricultural Imagery Program and also high-resolution elevation data, and in particular today, we're going to talk about LiDAR. We're working on an integrated topological correct data model, and the concept is that on this base map of image and elevation, we will put important resource information as well as conservation information about agribusiness. So in basics, a geodatabase is a combination of map data and business data. What is LiDAR? LiDAR is light detection and ranging. It is a 3D mapping system that provides information about the surface of the earth, vegetation, and man-made features. On the left here, we see some farm field boundaries, which are these really nice straight lines, and these nice smooth lines that mimic the slope of the land are actually terraces, and then these areas here are water bodies. So they call this a shaded relief product, and that is a derivative of LiDAR. How does LiDAR work? It shoots a laser beam from an aircraft, and like a flashlight, it'll shoot light between trees, branches, leaves, etc., until it can hit the ground. So for each LiDAR pulse, you're going to get multiple returns for the same area. It's very valuable information in an XYZ method. How does LiDAR work? LiDAR is a very active system. It emits a laser pulse which travels to the surface of the earth at the speed of light, and when they're reflected, that time it takes to get back to the aircraft is measured, and that's what determines its accurate z-value. The sensor determines the distance by measuring the time of flight in the pulse, and LiDAR is very accurate. It can be anywhere from 5 to 15 centimeters vertical accuracy, plus or minus. What makes LiDAR very accurate? It's tied to the government's Global Navigation Satellite System, GNSS, and it's also tied to ground base stations. And these base stations are set upon an accurately known fixed location, and then that information is transferred to the International Measurement Unit, and so it keeps track of where the aircraft is at an altitude, and as it flies on its course, it keeps track of its distance above the ground, and so when the laser shoots and measures these values, it becomes a very accurate system. A major advantage of LiDAR is, like we mentioned earlier, is that this laser beam can penetrate through canopy where light can reach the ground. That's opposed to photogrammetry, which is a more traditional technique, and he requires multiple views from photogrammetry, where LiDAR only basically needs to see one view to get an accurate measurement of the ground and of the canopy. Here's an example to us from our partners at the Forest Service. It shows the laser light going through the trees. It's striking the different branches, the leaves, the vegetation, and then ultimately the ground. The first strike is often called the first return. Leaves and branches will be the second return, the understory the third return, and generally the fourth return is what we would consider ground. What's neat about these pictures right here, it shows that they're showing the tree in 3D, and then it's colored by, on left, it's colored by the height, so red being the highest, blue being the lowest. And then on the right side, it's by its return number. So as we noted here on the left, there's multiple returns that make up this tree in 3D. There's another example, a different tree when you're looking just at the points in a cross-section, and it's showing that for each laser return, you're going to have multiple returns that tell you valuable information about how the ground looks and also a volume information about the tree itself. LiDAR makes mass points. It's kind of like a shotgun blast of laser beams. So these points are indiscriminate, and they shoot across the landscape. That's called a mass point. If you're interested in very dramatic, sharp breaks and features like a water body or a shoreline, you actually have to digitize extra features called break lines that show these transitions between the water and the land transition. On the right, here's a way where we would show our mass points in 3D mode. This is called the triangular irregular network, and TINs are irregularly distributed nodes and lines with 3D coordinates. So each one of these mass points would then be represented by one of these nodes on the faucets of this. And basically this creates a surface that gives your data that 3D appearance. What is a DEM? Points are often converted to DEMs. Each cell represents a unique XYZ value, and NRCS uses DEMs with many different cell sizes. We get data from the U.S. Geological Survey as part of their National Elevation Database, and the cell sizes come to us in 30 meter, 10 meter. We often get radar data from IFSAR at 5 meter. And what's very interesting these days is the high resolution data, which we would call less than 5 meter. So you often see LiDAR data portrayed in DEMs at 3 meter, 2 meter, and 1 meter is generally our finest resolution. On the left, they call this a lattice. This is a much more complicated mathematical surface for representing a surface. So NRCS uses the DEM grid on the method on the right, which is very more simplistic. So each one of these cell blocks would represent a mass point. Here's a picture of how you can separate bare earth from the ground and the first return. When NRCS first started using LiDAR, we were very interested in the bare earth last return, and that was very useful for terrain mapping and hydrologic analysis. But it turns out that the biological community is very fascinated about what information occurs above the ground. So we saw the first return and the second and the third return are telling you something about the canopy. And in this particular scene, you can actually see fields that are bare, that are represented, and then fields that have heavy vegetation or trees on them. And then that shows up in the surface model, and that kind of information can be measured and quantified and put into different kind of models, which is very, very. Here's another representation of DSM and DTMs. So the image on the top, again, shows the trees. The area on the bottom shows the DTM, which is often called the surface model. And the question is, do we need hydro enforcement? That goes back to the question about what is a break line. And a break line is going to show a hard break surface of transition between water bodies or other man-made features like roads, etc. On the left, we have an example of very high-density LiDAR collection. This is from Oregon. We have data expressed in different quality levels, and this data from Oregon is one of the highest quality levels you often see. You can have as many as 8 different points per square meter. And from that, then you can see some very interesting detail. These lines here would be a power line. These are areas here. These trees are along a golf course. And then these outlines represent the different buildings. They call this a shaded relief map. On the right, they also have an intensity raster. So in addition to XYZ values being recorded by the laser beam, you're also recording an intensity value that's often shown as a geotip product. And this intensity tells you different things about the surface that the laser hits. So here, this nice smooth surface area in this image in the hillshade translate to this light and dark, which turns out it's a river. And the vegetation also showing is dark areas where bare earth ground or the tops of buildings have a much higher intensity value and show up more white. It also turns out that LiDAR is absorbed in water, so generally the water is flattened because the XYZ values in water for this kind of laser is not very accurate, but it's very accurate for the ground. Here's an example of some of the things you can do with LiDAR. That over here on the left, we see a traditional high-resolution imagery, like from the National Agricultural Imagery Program. And so this is a natural color image. This scene in the lower left has LiDAR points draped on top of the image, and each color would then represent an XYZ value, where red would be very high, to orange, to yellow, to green, to blue would be going downhill. LiDAR is very useful for archaeological type activities. So something that's basically obscured in the trees, like there's a tree here with a shadow over this part of the image, notice that the LiDAR doesn't have any problem in detecting where this archaeological feature is within the image. So this image here on the right then is what we would call a tin that we talked about earlier, and it very well shows the LiDAR points in a 3D perspective. So with LiDAR, you often get much more than you would see in an image, that you're picking up some extreme detail that would be obscured from the trees. From this image here, you have a hard time telling that there's any kind of depression here, but the LiDAR sees through the trees, and you'll be able to see this depression quite well. USGS topo maps, we've been using them for many, many decades, and they're being replaced. So this is a traditional topographic map from USGS at a 10-foot contour. And here's an example for Kansas, where on the map, on the left, it's a historical analog topographic map. And those contours are no longer being drawn by cartographers because it takes too long, it's too expensive. So on the right is an example of contours that are generated from elevation data set. And last but not least, here's a more modern conservation plan map that you would see from NRCS now that has LiDAR's contours at 2 foot. So USGS contour maps, generally you see them at 5, 10, 20, and 40-foot contour intervals. And the contour maps NRCS is making from LiDAR are generally at the 2-foot interval. So this is a 2-foot contour map displayed on shaded relief map. For further information on understanding the basics, here's 2 excellent reference manuals. On the left is the Digital Elevation Application Manual from Dr. Dave Mowney, and this is a new book on the right, Airborne Topographic LiDAR, edited by Mike Renslow. Excellent reference manuals. and you can get those from Amazon or the ASPRS bookstore online. Here's the different quality levels that we have for LiDAR within NRCS. This line here shows that generally we're trying to work within the quality level 2 level to support conservation, planning, and design. Here's a map that shows where we have LiDAR readily available for the U.S. NRCS participates in the National Digital Elevation Program, and we cost share with our partners with USDA, FEMA, and the state and local to buy LiDAR in a partnership. And as you would notice, for the lower 48 states, we have approximately about 1/3 of the country readily available. And that's the end of my presentation. Thank you very much.
Okay, hi. Good, you can hear me. I'm going to talk about contour lines. Contour lines are the most typically used elevation data, and they have been for a long time. So let's get into it a little bit here. First of all, 3 parts of the presentation here. Benefits to using contours is the topic, and applications. I'm going to talk about NRCS work in particular. Hopefully you can draw some parallels. We do a lot of structural design in NRCS, and you can see from the picture there's a handsome guy out here in the field, and he's taking field measurements. And then there's a woman sitting at her desk, and she's happily working away without having to get her boots muddy. The idea with the LiDAR data and the contours is that at some point we won't have to spend as much time in the field doing this kind of work. So here I'm talking about, since I'm from Massachusetts and a lot of our work it has to do with Cranberry Bogs, this is the first example. It's a bog down in southeastern Mass where we have a water flow problem. Most of the water flow for this bog, with cranberries, you have to flood out at certain times of the year. So they're taking water from this pond, they're putting it through this bog all the way before they can get to this bog. So the project that they're trying to set up here was to create a bypass so they didn't have to go through this bog anymore, and they're going to go up around here, they're going to dig a ditch so the water could come directly to this bog down here. Problem was that over here we had a historic mill, which was a cultural resource, potentially a cultural resource. So they had to do set up the design for this really fast. Here's, like Steve was showing us, what we had for elevation data before the LiDAR data came around. That's one of those USGS topographic maps. We could see an elevation at the X of about 40 to 50 feet. Next slide shows, well, for Massachusetts at least, we're lucky we have a huge data set of data points for elevation. And in the next slide, when it eventually comes up, you'll see that we have a little bit higher resolution contour data available at our disposal, but still not quite as good as, this is taking a long time, as good as what the LiDAR can deliver. So there's the digital elevation model. Oh man, these slides are slow loading. There's the high-resolution Massachusetts topo data. That's one step up from what we had in the USGS topographic maps. Helps us to see a little bit more of information in the site than we would have seen in the topo maps. And the next slide is what we have from the LiDAR that we had collected here in Massachusetts. This is kind of what Steve was showing us. It shows the digital elevation model, where for the bog, where you can see the outlines of the actual cranberry cultivation area in yellow, and we have all the bare earth, which is like the fourth return of what Steve was talking about, showing up there. The green areas being the highest, representing the highest, and the low areas being dark purple areas. You can see right where the water flows through some of those easily in that picture. Next picture shows us what we finally were able to achieve when we flew the site with LiDAR. These are 2-foot contour intervals, a major step up from what we had from the USGS materials. So from that information, I took we extracted out the most relevant contours for this particular project, being the 45-foot and the 50-foot contours, and that's where you can see where our work actually happened. There's a little bit of a zoom right into there. So from there, what we did was we used that data, we exported that data into a pretty typical software set called Civil 3D, and from there our engineers were able to run this whole site into their design software, and there you see the drawing that they did zoomed up just to show you the map. The drawing's on the bottom, what they did, and then this is the zoom where you put, there's the ditch, it's going to come through. They're going to do some fill in here, and the water's going to flow right back down here. And the whole design was done without ever going into the field. Another nice feature here is that they can quickly, being able to quickly obtain the 45-foot elevation there, they're also able to design here the channel bottom. You can see it here in the, or the dike top first, and then the channel bottom here, you can see how easily they were able to do that. It's worth mentioning that these kinds of depth surveys also allow us to design these things in terms of real-world elevations and not relative elevations like we get from the total station survey equipment sometimes. So when we see 45 feet here, we know that's the actual 45 feet in the world and not just on the relative to the other sites, the other features on the site. Okay, so now I'm going to talk about wetland restoration, because that's something we do a lot of here. In the pictures in the slide, you see the first top left, you see an old culvert, and then in the middle of the slide, you will see a restored culvert where the water flows in and out of the nice marsh very easily. We do a lot of these restorations because when the old culverts were installed a long time ago, they stopped a lot of the natural flow of the tides, and that had a big impact on the ecosystem up above. So by restoring the flow, the salt water getting in there helped to fix that. So here's the old information we used to have. You can see on the topo map that Steve was showing us. Here's a site that we're very interested in. Here's the water flow, and there's the culvert right there under the road. Hopefully you can see that. Zooming in a little bit, you can see that the old elevation data only gave us these two strata to look at. There's a house on that site that you can see in the next slide, and that's the house that we were concerned with when we started our restoration work, because we knew that if the water rose too high after we restored that culvert, that house could be flooded out. And then you can see coming up next, when it eventually pops up, the digital elevation model that was derived from the LiDAR data. Blue areas being the lowest, red being the highest. The next slide that you'll see is going to show you the LiDAR-derived contours, once again, as we've been talking about, thrown on top of that. And then you'll have the 9-foot contour being the one that we realized was the lowest possible or the highest possible elevation that we could get to before we actually hit the house. So if that culvert was restored, we would know that as the elevation worked, as the water level worked its way up from 4 feet to 5 feet, 6 feet, 7 feet, 8 feet, everything would still be fine. But as soon as the water level got up to 9 feet, people like this poor fellow would have their basements being flooded out really fast. So the tool allowed us to really assess those kinds of damages on sites like this. And the next slide shows us the same kind of analysis, but for an entire neighborhood, where we removed the dike at this restoration area and restored the flow to all these, the natural flow to all these bogs, or former bogs and wetlands. And when we did that, we realized that this blue line here, the 10-foot LiDAR elevation contour, was going to be the highest possible water level when the site was restored. And the analysis helped us to highlight which properties would be the ones that could potentially be impacted. That's the parcel data, and the green hash marks are the areas that we need to be concerned with. Okay, last little section. Again, we're talking about LiDAR contours. And sometimes we do need very accurate information at precise locations. So I'm going to show a few examples of where the contour data gave us slightly different results than we would have gotten from the surveys. Once again, I'm talking about a cranberry bog. Hopefully you guys can draw some parallels to your work. We have our colleague Julie out there on this bog measuring all these different spots for elevation. When she did that, and what's typically done by the engineers in these situations is an interpolation of all those points to create a single surface of elevation. And that's what you see here in the red lines. That's the interpolation of all those points into a digital, contour lines. But when you look at the black contour lines from the LiDAR, you see a totally different picture and a more accurate one as far as what the site looks like. That's the first point I want to make. In that case, you would argue that the LiDAR data gives you a better picture. Now here, this is the second part. This is where you compare the actual values that are coming out of those, and it's pretty fascinating to look at. There's 3 actual cross-sections here. Each one has a number that corresponds to where it is. So, as you work your way along these 4 or 5 different points on cross-section 1, 2, 3, 4, 5, you can see that the elevations, these are the increments on the y-axis here, are 1 foot. Some of the areas here have actually like a pretty large gap between the red being the survey data and the black being the actual LiDAR data from the elevations. So that shows us that sometimes we get some different results, and that can be a problem. It was pretty cool going through this analysis because when I started asking about those with the person who actually was out doing the surveying, she showed me that these are the sites along these transects that were actually full of water or really high vegetation. And when you fill those water levels in that she measured, you do bring those values a lot higher up to where the actual survey data or to what the LiDAR actually read, because the LiDAR has a hard time penetrating water and high, very dense vegetation. So just to sum up my slides and stuff here today, we're talking about contours and when they make sense. LiDAR-derived contours make sense when you need to more quickly provide accurate information, like we did in the case of the old mill there that had to have a cultural resource evaluation and quick before the engineers could actually do the design in their shops or in the field. Sorry. LiDAR-derived contours make sense when you want to help project planners identify the potential impacts of a proposed project, like the high water in those 2 sites where we were restoring the wetlands. Did that without even having to go out into the field. LiDAR-derived contours also make sense when you want to identify optimal locations for more accurate land survey data, while still getting the big picture, real-world elevations of the site. So, and it will help us to decide whether or not we want to actually go out and do those kinds of surveys, as opposed to just using that come out of the cam of the LiDAR.
Great, thank you very much. And would you now promote, let's see, Reed? Thank you.
Hi, everybody. I wanted to show you a picture of old USGS 30-meter elevation data. This is what we used to have. We used this data for more than 20 years. And you can see broad areas of information and elevation change. The color areas showing white as lower elevations and green and darker green as higher elevations. But really this type of data requires field visits to see what's really happening on the land. Here's 1 meter LiDAR data, the same location and at the same scale. The red areas being the highest elevation and dark green areas lower, all the way down to white and light blue areas. As was mentioned before, LiDAR data is a point cloud, and it's not always useful until we make derivatives from it. Here you see the bare earth derivative, and Steve Nechero talked about that. These are the last returns that came back to that laser receptor. on the airplane. It represents points that hit the ground. And software that allows us to pick out sets of data exists so that we can choose just bare earth or just the top of the canopy, for instance. ArcGIS was used, that software was used to make a hillshade derivative from this bare earth DEM, and I'm showing it on the next slide. That's a hillshade derived from LiDAR, 1 meter resolution. Notice how the cliffs pop out. Back in the previous slide, we saw shades of darker green and white, but we didn't really know what that means beyond the fact that dark green areas are higher elevation. But a hillshade is a grayscale 3D model of the surface with the sun's relative position taken into account for shading the image. This function uses your choice of the azimuth and sun angle properties to specify the sun's position. The default for that is from the northwest, the sun azimuth from the northwest, and a sun angle maybe at 45 degrees. That's what we see here. But you can vary that as you need to in order to illuminate sort of and get shading in a different way for features that perhaps are in full shadow that you can't see otherwise. That information is really there still, and shining the sun, let's say from due east, would illuminate maybe some rough terrain right at the base of the cliffs, for instance. The sun angle, you can kind of vary it to what you see in the late afternoon versus areas you would see at high noon, for instance, or other times of day. What are these? Broken bridges? Actually not. This LiDAR data was prepared with all the bridges or other false obstacles where the water can actually run right beneath them, cut through, so that the software can simulate floods and hydrology that won't encounter a fake barrier. You know, the water would have run right under those bridges. The preparation process is called hydro enforcement, and you pay to get that process done. We usually pay for it before delivery, so the contractor does that operation. Here are some gullies. They were visible in slide 3 with the colorized DEM, but in that slide they looked more like streams. We can see a floodplain which is bounded by another set of cliffs. And roads show up pretty clearly in hillshades. Our engineers have used LiDAR data to help with surveying near roads they can't easily cross, like the interstate that's shown here in this image. Just south of this location, one of our engineering techs had to get across that for fields of the same farm that were downhill but across the road. And he used LiDAR. We used LiDAR data to get him data so that he didn't have to run across in the strength of traffic or anything. In the lowest corner of the left corner of the hillshade, we see an area which might be a quarry. On the next slide, let's look at the same area using an aerial photo. And historically, and still really, we use aerial photos to do a lot of our landscape interpretations and our conservation planning. We'll see how adding LiDAR data to an aerial photo increases the information that we can get from the photo. Okay, this is the NAIF imagery. That's imagery that's always flown during the growing season, and our sister agency, the Farm Service Agency, uses it to assess what crops are being grown during that year. Okay, this NAIF also has a 1 meter resolution, just like the LiDAR data did. Let's recall the hillshade. Okay, the cliffs show up again, clear as day. On the next slide, let's look at the same area, adding an aerial photo. The air photo contains geographic coordinate information, and that is we know where the houses or the roads or the trees are on the planet. The hillshade also contains that geographic information the same way. And Aaron alluded to that with his references to where we engineers sometimes use a total station and get relative elevations. These are real ones with regard to sea level. Now we've overlaid the photo as a transparency on top of that hillshade, and the result is an air photo which has some 3D information. We can see the trees are growing on and below the cliffs. Thus we know the shape of the bare earth and what exists on the earth, the land cover there. Okay, I'm going to switch to showing hillshades and how they're used to identify gullies. The areas which are within the black line polygons here and appear relatively flat are crop fields. The blue line is the Rock River in northwestern Vermont, which winds its way between the crop fields. Now we'll get in a bit closer. The Rock River stream bank has gullies which are encroaching on some of these farm fields. Left untreated, these gullies will create significant problems for the farmers. The LiDAR allows a conservationist or someone who's maybe with a river watershed association to see the gullies earlier than they might otherwise, before they do a resource assessment even out on the field. And seeing these encroachments in GIS might prompt us to visit the field with GPS devices, find and evaluate those specific gullies that we saw in the LiDAR data. This gully is so small it may not be visible on a field visit, and especially during the growing season. We've got the corn up. There's just no way that will show up. However, using its geographic location from the LiDAR hillshade and a GPS, the field conservationists can readily find the area and discuss appropriate treatments with the farmer before the gully becomes a problem for that farmer. Also notice the thin blue line stream at the lower right, and see if you think that is really the center line of the river here. Now we turn to stream location. Stream locations are, of course, very important when helping farmers and landowners to assess the need for conservation practices. In the following case, we have a dairy farm in Vermont. The tan arrow points to a narrow blue line, which is a stream, according to older data. It's actually the official Vermont streams data. So was that line so was that line you looked at in the Rock River. That's official Vermont data, best available. This blue line cuts across the area as if it were an above-ground pipe. That is, the area around the blue line doesn't look like a stream bank. We can zoom in and see the spot more clearly. The narrow blue line shows where the less accurate older data locates the stream. It doesn't look like the blue line's correct, but is it real clear to you where the stream really is in this case, or how pronounced the swales or banks are? Looking just at the hillshade in the same place, now the tan arrows are pointing to a depression, and this is visible because of shadows. The depression is a stream which has been straightened. We can see that the actual stream is a bit further from the barnyard than the old hydrography or stream data showed. Now, in this case, it might not make a big difference to evaluate the danger from barnyard runoff, for instance, but there may be farms where the older digital stream data can really mislead us. I noticed one spot in the same watershed where the old stream data was about 200 feet from the actual channel of the stream, and it was partly because there were a lot of trees in the image, the aerial photo, and you couldn't see where the stream actually went. So to summarize this section, where LiDAR-derived hillshades make sense, I want to emphasize the most that you can use them to understand the landscape before visiting the field. It gives you the whole picture of the farm, the steepness. You don't have to evaluate that quickly as you get out of the truck and the farmer's heading toward you. When you want to help farmers anticipate future problems, like those gullies we saw encroaching on a particular field, or when older GIS data don't seem to make sense anymore, you can use LiDAR to assess whether that's right or not. Thank you very much.
Thank you, Reed. So can you make Steve Crabtree the presenter, please?
I will do that.
Thank you.
Okay. I'll get started. The example I'm going to show you today is how we make practical use of these LiDAR derivatives that we've been talking about. And what I'm going to do is run through on how we use LiDAR to design a grass waterway to correct an erosion problem on a farm. So when we design a grass waterway, one of the most important things that we need to know is the peak discharge. So the question becomes, how much water are we dealing with? Without LiDAR, answering that question required doing these 4 steps manually. We had to determine the watershed boundary, the watershed slope, the watershed flow length, and the watershed curve number, and we're doing all of this in a manual method, just really making estimates with the best information that we had. So how can we improve that with LiDAR? Well, we're going to use a GIS tool. We're going to demonstrate how we do that, where we utilize these very accurate LiDAR derivatives to get the answers that we need. So we've set up a model to do that. Now, even though it's a complex model, it's very simple for the field staff to run that model. And then most important, the results that they get are very accurate information for estimating this peak discharge to build this waterway. And it's a huge time saver for the field folks. Okay, for LiDAR to make sense in the field office, for a non-GIS user out there in the field office, it must be provided in an easy-to-use form. And this hydro tool that I'm showing you today for calculating peak discharge, it's an example of where we're making practical use of LiDAR. So we're going to get an accurate calculation of that discharge, and ultimately that's going to be a better engineering design for that conservation practice. So again, what we're going to do is use LiDAR to help us with designing a planned grass waterway, and specifically the first thing we need to do is do the peak discharge for where that waterway is going to be built. Now, when I use the term LiDAR, the other folks have talked to you about some of the derivatives such as contours and hillshade, aspect. The model that I'm going to show you doesn't use those, but it uses the top 5 there in the list. And when I use that term LiDAR, I'm really referring to the very accurate derivative products that LiDAR gives us. So I'm going to give you a quick overview of the ones that we're using to do peak discharge. Of course, as Steve Nechero talked about, the basis of our elevation data is the DEM derived from the detailed complex set of LiDAR bare earth elevation points. Quite simply, LiDAR DEMs give us very accurate elevation data. Now, from that base DEM to do hydrologic modeling, we need to have a data set called flow direction. Flow direction allows us to more accurately predict the water flow through computer analysis. Closely associated with flow direction is flow accumulation. That helps us easily visualize the areas of flow accumulation. So what you have here on the screen is just a zoom in of a computer depiction of virtual streams or areas of concentrated flow. So again, we're using this to accurately predict our water runoff. Now, another pre-developed LiDAR product that we're using in our model is having these what I call watersheds from LiDAR polygon features in our as a GIS layer. So here's an area, 100,000 acre area of LiDAR coverage, but we've broken it down into small sub-watersheds, ideally 50 to 1,000 acres in size. Now, this allows for a much faster geoprocessing. These data sets are extremely large, so this is important that we're going to do our analysis within these sub-watersheds. It's all about computer processing time, so this is really going to speed up our analysis by having these small sub-watersheds. Okay, we also create a slope data set from our LiDAR, and LiDAR slope, it just provides an extremely accurate average slope for our watershed. So, for instance, if we're going to build a grass waterway and it has a 55-acre drainage, the tool is going to tell us, for example, it might have a 4.3% average slope. We know that's extremely an accurate depiction of that slope based on our LiDAR input. Okay, besides the LiDAR data, there's a couple of other data sets that we use in GIS as part of our analysis. One is soils, our Sergo product. We're using the hydrologic soil group for the soils. We're using that as part of determining our runoff curve number for the watershed. Also for runoff curve number, we have to have a good land cover source. So for our watershed, you know, what is it? Is it cultivated crops? Is it pasture? Is it hay? Is it forest? The National Ag Statistics Cropland Data Layer is the land cover data set that we use in our model. And again, working along with soils and slope, this helps us determine that runoff curve number. So that's a quick overview of the inputs to our model. And quite frankly, the model is fairly complex, but the key is it's very easy to use. So we've taken a complex set of GIS processes and we've put them in a very simple tool. I call this my training slide. All the user has to do is zoom in and click on the planned outlet point for the grass waterway. After they do that, they either accept the default for good hydrologic condition, or instead they would select either fair or poor for the overall condition of the upstream contributing watershed area. If you designed a practice, you'll understand what I'm talking about, is that's part of the design. But really that's all they need to do. So it's very simple. They just click on that outlet point. They're usually going to accept the default and just hit OK. Now, this slide shows the ease of getting the results. Now, the field staff did not have to do anything. They didn't have to draw anything or make these labels on the map. In ArcMap, they get the answers that they need directly on the screen. So if you're familiar with designing a conservation practice, you understand that the design requires these 4 pieces of information to estimate your peak discharge. You've got to have the drainage area, the slope, the curve number, and the watershed length. It's all displayed in 3 to 5 minutes on the screen, and more importantly, it's extremely accurate. Now in Kentucky, we use this Engineering Field Handbook, Chapter 2, to actually get that final peak discharge number. And EFH2, it requires those 4 results that we've already gotten from LiDAR. So we simply go in there and the user takes about 30 seconds to input those 4 values from the ArcMap screen: the drainage area, the runoff curve number, the watershed length, the watershed slope. And on the next screen, he simply selects, for instance, a type 2 rainfall. We're going to design this grass waterway on a 10-year frequency storm. This is our answer: 80 cubic feet per second of peak flow. So we've taken really a very complex process that would take, easily 2 to 4 hours, depending on the drainage area, to do this right. And then you still don't have, you're just making estimates by doing it from a manual method. So we really think we've got something that's easy, accurate, and practical. Now, we have tested this extensively using some of the older DEMs. You can see here there's some differences. They're not real big differences in this site on our end result, but usually we get a vast difference in our calculations, and we really don't encourage using this method with older DEMs. We just don't trust it. I mean, again, if you've got really good inputs going in, you're going to get a really good result coming out. When you compare it to the manual method, you can really get big differences. The manual method here resulted in 34 cubic feet per second peak flow. The 1 meter LiDAR resulted in a higher 80 cubic feet per second peak flow. Now, the important thing to point out here is this is an actual NRCS-assisted grass waterway. It was designed to carry 34 CFS using manual methods. But with LiDAR, we would now design the grass waterway to carry 80 CFS. Quite a difference. So what we did, we manually designed and built a waterway which really needs to carry almost 3 times the amount of water that we thought it needed. Is the manual method, is it going to fail? We didn't have enough rainfall last year to know, but the erosion problem may not be solved long term. So obviously, a design based on LiDAR GIS is better. For the investment, the LiDAR design practice will last longer than the manually designed grass waterway. Again, it's an easy thing to do. It's, if you have a tool put together that the field can run, they don't have to be GIS experts to run these tools, and it gives us a good practical solution. Now, in the future, these are really big data sets, and the hope is that eventually we'll move this data to the cloud. We'll have a web server-based application that hopefully down the road the district conservationist and conservation desktop will click on his screen. These results will be run remotely and delivered back to him. So that's where we're headed, but certainly the potential to make good use of this excellent data is there for us.
Thank you very much, Steve.
Okay.
So we now turn it over to questions. So there were 2 questions that came into the notes. So Aaron, during your presentation, Rebecca wanted to know, how do you label the contour lines?
Let's see, can you hear me? I hope you can.
Yes, we're just open.
How I label the contour lines?
Yeah, Rebecca wanted to know.
When the contour lines are generated from the digital elevation model in ArcGIS, there's an attribute field in the shapefile that we created shapefile, and then ArcGIS just has a function where you can label the lines based on any attribute in the database there. So
great, thank you.
Yeah, it wasn't too complicated.
And Steve Crabtree, Bill Prince wanted to know, how do you know the slope is very accurate? Like, do you take the total length and divide it by the fall in the elevation, or another method?
Well, that's part of the computer processing. We've got the low point down at our outlet, and then we've got an overall depiction of the entire watershed. For instance, that was a 51-acre watershed that I showed you. We've got detailed elevation for every square meter within that 51 acres. So the computer processes using GIS analysis does an actual calculation. It's not an estimate. It's an actual calculation of all of the pixels within that 51 acres, and that's the average slope from top to bottom. Very accurate.
Great. Now, moderators, can you see the question from John Dasgate? presenters? I guess.
Yes, Madeline. Yeah, we can see it.
Who would like to take that on?
Well, this is Reed.
Go ahead.
This is Reed Sims. John, you're asking what type of smoothing do you use to generate a DEM that's not quite as, doesn't have as much micro topography. And there are some smoothing functions within ArcGIS. One is called fill basins, I think it's called. And to tell you the truth, I tried that with an old machine running Windows XP, and it worked for about 15 hours or so and crashed. So I know that's the method that is used, but I have not had any success actually doing this yet. That's what you would do if you had a Cray supercomputer and could do it all at once.
One thing I would like to add, and this is kind of technical, and you can certainly talk to me later, but Dwayne Daniels from Fort Worth was a lot of help to me on some of my LiDAR analysis when I was getting started, and I ran something called focal statistics on my LiDAR data set to do that smoothing that is referred to in the question, and I got a lot cleaner result after doing that, and I can talk to you about that offline.
Let's see, Gail Myers. Wow.
Yeah, that is the pour point. The planned outlet point would be what you would refer to as the pour point, the bottom of the flow area.
Okay. Let's see. My goodness.
I'll chime in and help you out a little bit, Madeline. Here's a question from Jack. He states that Upper Michigan shows no LiDAR data available. Will that change? Is that something that y'all can weigh in on?
Sure. This is Steve. Can you hear me? The NRCS is participating in the 3-depth National Elevation Program sponsored by the U.S. Geological Survey. And there's a 10-year plan to try to complete LiDAR for the lower 48 states. The project is just getting off started, and right now we're working on a project-by-project basis on trying to build LiDAR projects for the individual states. So in Michigan, if you would work with your USGS liaison, you can help get your project started for the Upper Peninsula. Thank you.
Thank you, Steve.
I think Brant's question is very similar to that. I'm going to read the whole thing, but I think the additional part to his question would be how expensive is it? So he states, if MAP is showing no LiDAR available for part of the state, is it possible to get it? And if so, how expensive is it?
LiDAR costs vary anywhere from $100 to maybe $1,000 per square mile. It has a lot to do with the quality level that's picked. For example, NRCS buys quality level 2 LiDAR, which will support a 2-foot contour. And generally, you're looking with all the bells and whistles of the derivatives mentioned by the speakers today, it's right around $300 to $500 per square mile product.
Steve Nechero, do you see Sam's question? Seems to be along the same line. I think the difference here is the specification of LiDAR 1 meter resolution data.
The conversion of LiDAR point clouds into grid product, it depends on the nominal pulse spacing, how many grids per meter, and also the vertical accuracy.
It's good. Yeah. Do you want to, do you do grass watering?
Yeah, I mean, everybody does it.
Okay.
Yeah. Come on, it's on the size.
Okay.
Sometimes the technicians can do it.
Okay.
Based on the size.
Okay.
Are we still on?
Yeah, I think
yes.
so.
Someone has their someone is through even though they're supposed to be muted. And I'm not sure who.
So the question on the 1 and 2 meter, what's readily available, if you visit our Geospatial Data Gateway site, there are status maps that will show where there's 1, 2, and 3 meter data readily available. Right now it's a small collection, but it's growing as fast as we can process the LAS point data. If the person that asked the question would like to send us an email, then we can follow up later.
Okay, we have a lengthy, doesn't seem like, well, the question doesn't seem to be obvious, from Hill. So, oh my, wait a minute. This is scrolling from Hill Brian. And he's talking about how using LiDAR could be reducing the number of jobs, and one reason folks join NRCS is for the field work. And the wetland example, you know, about the flooded basement might occur even before 9 feet. Let's see, an example ditch. I wonder, Hill Brian, if you're still on, could you join us and express what your question is?
This is Steve Nechero. I think I could kind of get the gist of this, is that LiDAR is a remotely sensed technology, and it is designed to supplement and not replace field work. So there is still a business requirement and a scientific need to do field work. So LiDAR doesn't replace field work. It basically enhances the capability of the person that's in the field. But there are many applications, and some shown today, where instead of doing planning work or some analysis work that would require an on-site visit, it can be performed in the office. But we still fully intend that we're going to have personnel with boots on the ground.
This is Reed Sims. I'll add that our engineers were excited when they could use the LiDAR data for bigger areas around, let's say, a farmstead, looking for runoff potential, et cetera, but still retained the thought that they should do their total station work right at the farmstead within the barnyard, because they trust that more than, you know, they didn't have much experience with LiDAR yet.
I'll add one thing on the accuracy. I'll talk about our state engineer since he just retired. But we won him over on a site that we did as an example that bordered a highway, and there was a 6-inch crown in the middle of this highway, and the drainage area was delineated right down the center of the highway, as it should be. So LiDAR was able to depict that drainage that accurately.
Okay. Let's see, this notes page seems to keep scrolling. So anybody know what the next question is? Is it Michael Bobek?
Yeah, I think you could go ahead and address Michael's question.
Okay, great. So how soon will the instructions for the watershed analysis roll out to the states? And are there plans to include TR55 methods for urbanizing watersheds? Anybody got enough engineering to answer that? What I can do then is, Michael, is talk with our engineers here in the center and get back to you. If you would email one of us, is that possible for you to do? Because I understand there are folks on who are not from NRCS, and I might not be able to find you. So if you go on the NRCS website and you Google the East NTSC, East National Technology Support Center, Michael, then any one of us can help you get to one of our engineers.
Okay, Michael has responded that yes, he will do that. So that'll take care of his question.
Okay.
Okay, let's move back up. Bill Prince had a question, and his is, how do you know the slope is very accurate, and do you take a total length divided by the fall in elevation, or what other method?
And Holly, I think we did that one.
I apologize.
No, that's okay. This scrolling notes thing is really annoying. Okay, how about James Respapo? We're in the areas that was shown in the map of the U.S. that had LiDAR information available, and checking on the Geospatial Data Gateway in my county under the L3 files, a 3 meter, 10 meter, 30 meter. Are those LiDAR files, and if so, which one should we use?
The 3 meter would be from USGS, from the National Elevation Database, and that is derived from LiDAR. And when you order the product from the gateway, the metadata will tell you about the horizontal and vertical accuracy of the collection.
And the 10 meter and 30 meter are actually directly derived from the old USGS quads. The 10 meter, I think USGS has completed at least the continental U.S. I'm not sure about Hawaii and some of the other islands. But it's just, data that was available from those quads. That's what all the 30 meter DEMs are as well.
With the exception that where new LiDAR data exists, USGS went back and post-processed and resampled the 3 meter back to 10 and 30 meter. So if you're in the same geography and you've got 3, 10, and 30, the 10 and the 30 are just resampled versions of the 3. So it's just been generalized. So in theory, it should still be better than the legacy USGS topographic map.
Thank you, Steve. Ryan Stitt asks, how do you access the topmost layer in a DEM? I wonder if he's talking about the first returns in a LiDAR?
That's right.
So one way to do that is when you get an LAS point cloud, and that is an ASPRS format with different versions, the vendor classifies the points with the different return values. And then those return values are also then classified into different groupings based on whether or not you were trying to identify the bare earth ground, which is often class 2, class 8, and then classes 3, 4, and 5 tend to be vegetation classes. And usually the first return then is classified as top of canopy. So when you use LAS software and you ingest the LAS file, they, just like in the PowerPoint slides, they'll come in color-coded based on their return, and then you can also color-code them based on their classification. And so then you can run a filter to actually then extract just the first return or the points that are considered part of the canopy. So you need LiDAR software to be able to do that.
Thank you, Steve. So I'm scrolling back. Let's see, we have a follow-up question from James when he's the person who asked about the 10 meter to 30 meter, and he asked, how do you, which one should you use?
It depends on their application. Three meter would be best. If they'd like to send us a follow-up on that, we can contact them directly about their specific application.
That would be great. Thank you. Let's see. Mark Waschek, has anyone used LiDAR data to determine length and slope to use in a water erosion calculation in Russell 2? So I guess we can reframe that question. Have any of you used it with Russell 2?
This is Reed in Vermont. We have a young employee who is trying that out. Other older employees are saying they don't think it's going to be accurate enough, or that it really requires human decisions on where you take the top and bottom of a slope length, etc. So it's kind of in the process of being researched.
Great, thank you. Reed, do you think we should bring it up to the East GIS folks? See if any of them has tried this?
That's a good idea.
Okay.
Yeah.
So Mark, if you stay in contact with us, we meet regularly in the East among the GIS specialists, and we'll be glad to ask that question and get back with you if you contact us. Okay, let's see. Victor Slowick, when cropping LiDAR, what is the difference between cropping using extract by mask from spatial analyst from data management tools? Data management tools seems faster, but are there other differences? So we're cropping LiDAR data.
We'll have to look that up on support.esri.com and follow up.
I wonder if Dwayne Daniels might have. I'm trying to take some notes here for. Okay, let's see. Terry, how do we view the written questions? Gosh, Emily, how do they view the written questions?
I have just captured the notes from this session.
Okay.
So as a follow-up, Madeline, I'll ask you to kind of consolidate those questions, and we can provide those as a handout. We'll post those back up to conservationwebinars.net. So the same web page that you used to launch this event, you can return to it, and you could pick up a copy of the questions that have come in with the answers.
Great. Okay, Andrew Kessler, is NRCS GIS Hydro Tool you presented publicly available? Well, Steve, that's your question, huh? Steve Crabtree?
Yeah, I responded back to that guy directly. Yes, it is available. It's still kind of in work, but if they'll get with me directly, I can help them out on that. And we do, by the way, have a version. It works best at version 10.1. But for NRCS folks, we're using it at 9.2 or 10.0.
We have a comment here that background conversations are cutting off the speaker. It might have been when we had that interruption earlier. Okay, so Hill Brian, while waiting for LiDAR coverage, the Web Soil Survey can be used for hydrology information. It has a topo map background option. AOI area can be drawn in irregular shape on the topo background to delineate or measure drainage area, hydrologic soil group areas. So I guess part of the conversation here. Is there anything presenters want to respond to that comment?
I'll address that one. I don't know if that was an NRCS question or not, but in our NRCS field offices, we would have typically used ArcGIS to do that by bringing up the topo in ArcMap and doing it, with pretty robust set of tools that we could use at the field office to get those drainage areas. I think the point we're trying to make today is, that's outdated technology, because now with our LiDAR data, just the simple thing of delineating that watershed from a topo map, it's just not that accurate compared to what we can do with LiDAR.
Thank you. Okay, I'm down by Dennis Renkins. Oh, okay, I guess he has the same question about the upper peninsula of Michigan on data availability, LiDAR availability. Okay, Ken Owens.
Madeline?
Yes.
This is Reed Sims. I got a question directly from Melissa Allen that I'd like to answer for her as well. The question is, which layers would provide the most use to a beginning user? Bare earth slope, bare earth aspect, and bare earth hillshade? Should we download the elevation data set? Melissa, It probably depends, again, as Steve Nechero said, on the uses you might want to make of it. I would say a beginning user could make the most use of a hillshade and or contours. Those two are already kind of intuitive for most users, even beginning users of geographic data. After that, then you might start looking at specific applications and then ask someone with LiDAR experience which of those LiDAR derivatives you might need for that application.
Thank you. Okay, we have one here from Ken Owens. Can you derive first versus successive returns from last data? So Steve Nechero, you might point back to your slide on the forestry.
So that was similar to the earlier question, that using LiDAR software working directly with the LAS file, you can filter based on return or classifications to extract those points that represent the features they're trying to identify.
Great, thank you.
Can you do it in the new ArcGIS versions?
In ArcGIS 10.1, there is an LAS data set and new 3D tools that are available. Currently, NRCS is at version 10.0, so those are not readily available to us today. So I can't really speak to how well they work. NRCS tends to use third-party packages for LiDAR software analytics in addition to Esri software.
Okay. So Eric has asked about getting the continuing education credits, and so...
and I would say, Eric, to get those credits, we've provided in the notes the redirect link to get you back to conservationwebinars.net. If you use that redirect link, you'll come back into your own email address, and you'll just need to finish out the workflow that you initiated as you logged into the webinar.
Okay, we'll entertain two more questions and notes, and then we'll have to call it quits. Our presenters are probably really tired. Let's see, Sam Carlton, are overlays of aerial photos on a hillshade available publicly? If so, where? So can you get the product of the overlay?
On Esri Online, they're working on a world elevation service, and you can look at hillshades and high-resolution imagery. And then there is a transition tool or a transparency tool where you can do a slider bar. So basically you can drape your image on top of your hillshade, and then you adjust the slider bar on the image, and it gives that 3D appearance. And that is free and open to the public.
Great, thank you.
Visit arcgis.com.
Thank you. Okay, let's see. We got another. Holly, what should we do? Questions are coming in still.
Well, if our presenters are willing to entertain them, I guess we can stay on and keep answering. The main thing is for any of the people that needed to get out because of time constraints, and if you're wanting to get your training certificate or your CEUs, please use the redirect link that we've provided. That came out in the notes section from the AT&T operator. I guess we can answer a couple more questions, and then we really should call it a day, but we will capture the questions in our notes, and then we can post those in the handouts like I mentioned previously.
Okay. So any of the presenters who need to leave, please feel free to do that. Okay, so Peter Julovich has asked, can LiDAR be useful in developing pollutant loading from a particular watershed to a particular water stream?
This is Reed. I would say yes Peter, it can at least give us more information than we've had before, because a lot of the loading questions correspond to the speed at which water can get through the watershed and the amount that's going to hit any particular loading point or exit point from the watershed.
Thank you, Reed. And Natasha Spears, can the grass waterway EFH2 drainage tool Mr. Crabtree developed be made available to other NRCS states?
Yes, I'm just encouraging folks to call me directly on that, and I'm sending him a note now.
Great, thanks a lot, Steve. And Jeffrey Schoening, are 3D analyst and/or spatial analyst needed? Those extensions.
I just answered that one to him directly.
Oh, okay.
But I can say, just for the benefit of the group, that yeah, you need those extensions to pull the contours out of the DEMs, for example, that I was looking at in my stuff. But once you have those contours taken out of the DEMs, then you can do a lot of stuff without the extensions.
Great,
and I should have pointed out, this is Steve from My Hydro Tools, the spatial analyst extension is a prerequisite.
Great, thank you, Steve. And our last question from Lane Johnson. What GIS software will CDSI web application use? And will LiDAR DEMs be able to be used?
That's the question you were waiting for, Steve.
The short answer is that CDSI desktop applications will be consuming REST services, and NRCS has published them using ArcGIS Server 10X technology. And for internal NRCS and partner use, we'll be publishing LiDAR as the services that were demonstrated today. So you'll be able to see through a web service the surface model, the bare earth model, the hill shade, the slope, and the contours. The additional derivatives that some of the presenters talked about, those will have to be post-processed, and back to an earlier question, you'll need a spatial analyst or 3D analyst to be able to create those additional derivatives. So that's the current plan.
Thank you, Steve Nechero. And Holly, I'll turn it over to you.
One
question. I'm sorry. We might have been getting a little feedback, but I think
saying that a lot of the LiDAR data is being loaded up into a web-based tool that you can extract a lot of those things out of that coherent LiDAR server software. I don't know if you want.
Aaron, we could hardly hear you.
I can address that. In addition to Esri software, NRCS is exploring the possibility of using a product called LiDAR Server from GeoQ Coherent, and it is a web-based system that allows users to visualize the point clouds, express the points as tins, and also express the points as contours through a web browser as well as WMS web services. It's experimental at this point.
Thank you. So, Holly, you want to close it out?
I sure do. Thank you very much, Madeline, for moderating this event, and thank you to Steve Nechero and Reed Sims and Steve Crabtree and Aaron Dushku for giving this presentation. You can see from the number of questions there was just an incredible amount of interest in the presentation, and I must say that at 560 participants today, that's about 200 higher than we've ever had in one of our events before. So this was a very large and meaningful event, and we appreciate everyone's work that went into conducting it. Special thanks to our presenters, and my special thanks to Madeline for setting this up. So our next webinar is March the 13th. It's going to be a fun topic. It's about using social media to increase awareness on natural resource issues. So we encourage you to come back in and join us on March 13th for that webinar. And again, thanks everyone and have a great day.